Good day. Our exploration of super-efficient buildings is by far the longest in this course, totaling 2.5 hours, but it's broken into 3 bite-sized sections with the movie in the middle, so you can take 2 breaks, and this is the first section. Why should we take so much time to learn about buildings? Because they're familiar and ubiquitous, so they're the simplest way to introduce integrative design. Buildings also use nearly 3/4 of America's electricity and 1/4 of the methane gas. They emit 39% of US or 1/4 of global fossil CO2. They also emit 1/3 of the world's black carbon and 1/8 to 1/3 of the F gases. Buildings also use 2/5 of the world's materials and energy and 1/6 of the water. Just operating buildings uses half the world's electricity. Their locations also largely determine where we need to be and go, and therefore how much we must move our bodies and goods. And North Americans spend over 90% of the time indoors. So as Churchill said, we shape our buildings, and afterwards our buildings shape our lives. U.S. buildings are about 85% of the nation's total fixed capital assets. Buildings have the slowest turnover of any major capital stock, often half to 1 century. U.S. buildings split their energy use pretty evenly between residential and commercial, but globally 3/4 of their energy runs households. 1/3 of global buildings' 2010 energy provided space heat, 1/3 hot water, and 1/5 light. So cooling and other uses were relatively small, but set and starting to soar. So now you know why we pay so much attention to buildings. Now, about a century ago, we largely forgot how to design buildings optimally. The best Victorian architects integrated passive comfort and ventilation with daylighting, but then the design process got all chopped up and specialized and fragmented. Nowadays, 2 different architects or even 2 different architectural firms may design the same building's shell and its interior separately. But reintegrating the design process can achieve remarkable results. And we're starting our integrative design journey with buildings because, as you'll soon experience in the virtual tour of my home from which I'm filming this, buildings are the easiest way to illustrate how whole system design can make very large energy savings cost less than small or no savings if we emphasize not what's in the building, but what got designed out of the building. We all have our opinions about how well or how poorly buildings have evolved to meet the needs of their occupants. Victorian designs of zoos and of offices have often evolved much further toward naturalistic habitats for other great apes than for humans. However, our focus here is on energy-efficient design, which can vastly improve human well-being as a free byproduct of restoring the earth. Our buildings should, in Ray Anderson's words, take nothing, waste nothing, and do no harm. They should look like they grew there. They should create delight when entered, happiness, health, and productivity when occupied, and regret when departed. They should be flexible to adapt gracefully to unknowable future needs, resilient against future disasters, and designed for the last day of occupancy as much as the first day. Then, when they can no longer be converted to new uses, they should be designed to recover and reuse their materials and their site. They should be net producers of energy, clean water, beauty, perhaps food, and right pedagogy. They should cost less than now to build and far less than now to operate. If we rise to these challenges, we'll live better, do better, and save enormous amounts of energy, money, and harm. And we can achieve all these goals at the same time, without trade-off or compromise, and often at lower construction costs. Over time, the benefits greatly increase. RMI's 2011 synthesis called Reinventing Fire showed that by 2050, at historically reasonable speeds, U.S. buildings can triple or quadruple their energy productivity, saving $1.4 trillion net present value with a juicy 33% internal rate of return. That is, the energy savings are worth 4 times their cost. To make super efficient, zero or positive net energy buildings become the new normal, we need to shift the balance of the value proposition by making cost lighter and value heavier. Home builders and commercial real estate developers are skilled and tireless in seeking to lower the costs of labor and materials. They add new features to get market attention and add value. They also raise energy efficiency to give customers lower utility costs with greater health, safety, comfort, and environmental responsibility. Some builders brand these forms of value through standards like LEED, that's Leadership in Energy and Environmental Design, a very popular rating system that RMI helped the U.S. Green Building Council to invent and spread. 2 less common approaches can further raise value without extra construction cost. Integrative design, which can often reduce that cost, and resilient power, which often offers synergies that we'll discuss in Lecture 8A. Buildings use energy for many purposes. In the U.S., the main end uses are space heating, space cooling, lighting, refrigeration, residential water heating, and electronics. Of the primary energy used, the left-hand column, half gets lost in the electricity system before it reaches your meter. That's mainly because the U.S., unlike most industrialized countries, favors power-only generation, even though capturing and reusing the waste heat as well at the power plant could save 1/8 of U.S. carbon emissions and tens of billions of dollars per year. The rest of the energy gets delivered to the building after the dark red losses, and most of it is then wasted in the end-use devices, providing such services as visibility, computing, cooking, entertainment, and thermal comfort. That's the 10 HVAC or HVAC box, which stands for heating, ventilating, and air conditioning, provided by what's collectively called mechanical equipment. Now, primary energy use drives climate impact. Delivered energy use drives your energy bill. Either way, very efficient conversion and very efficient end use are the keys to effective, profitable, valuable, and healthful and pleasant buildings. Today, we'll focus on end use efficiency, which both saves delivered energy and avoids the upstream conversion losses shown in dark red. Reinventing Fire found that with concerted effort, the U.S. could run 70% more floor space in 2050 with uncompromised, indeed generally improved services, and yet use 58 to 72% less energy than those buildings would have used at 2010 levels of efficiency. That's 54 to 69% less energy than was baked into the official 2010 forecasts by the U.S. Energy Information Administration, EIA. Our efficient technologies findings, that's the 5th column from the left, come from a major 2009 report by the National Academies, which found that additional efficiency would cost 1/3 as much as the electricity it saved, or half as much as the methane gas it saved. As we'll see, there are now much better technologies, many not yet included here. Now, the next column, our smart controls savings, rely on detailed data compiled by the American Council for an Energy Efficient Economy. The range of integrative design savings in the right-hand green bar comes from actual building measurements. I'll show an example in a minute, but it's deliberately conservative and it's worse than RMI's practice routinely achieves. Now, before counting integrative design, all these savings would cost $500 billion more than business as usual in present value investments. It would then return $1.9 trillion in gross present value. Subtract 1.9 minus 0.5, that's a $1.4 trillion net gain or profit. And this conservatively assumes that integrative design saves more energy than conventional disintegrated design, but not at lower cost, as in fact it often does. We've shown a twofold range in that right-hand green bar of integrative design savings because the U.S. cases show a wide scatter in both savings and costs. That's because of differing skill levels in design and execution. So this adds uncertainty about adoption, but it highlights the business opportunity in taking high-quality integrative design rapidly to scale. Here's a little peek behind the analytic curtain, illustrating the conservatism of those reinventing fire estimates of what integrative design could do for buildings. We separately analyzed new and retrofit, fixing up old buildings, for both commercial buildings and houses. For new houses, our basic National Academy-based saving was 29% without integrative design, but 48 to 69% with integrative design. That's somewhat worse than our 77% best case for a house about as efficient as mine. You can see on the right-hand side the wide scatter in both the measured savings and their marginal cost. Again, differences in quality of design and execution using techniques that are often unfamiliar. This scatter makes the extent and quality and speed of adoption span a pretty big range. Yet for diverse houses approximating our high savings case cost nothing extra to build, or even less. And that highlights the business opportunity in rapidly taking best practice integrative design to scale. For the separate housing and commercial building analysis, we averaged two numbers, the average of the better half and the average of the worse half of the measured performance data. Obviously, using best cases would have given much bigger savings, but we were deliberately being conservative. And since that 2010 analysis, building efficiency gains have accelerated. Now, I'm speaking to you from my home and office where we incubated RMI for its first 18 years. You will next watch Lecture 2B, a movie, a virtual tour to consolidate these design concepts. It's a 372 square meter building, though actually it's all round meters, 2,200 meters above sea level near Aspen, Colorado, where temperatures used to dip as low as minus 44 Celsius. We had a whole lot of snow last night. Adding thicker insulation would add proportionate cost, but it leaves less heat loss to be saved by adding even more insulation. So the cost per unit of saved heat rises geometrically as you make the insulation thicker. Well, normally engineers add insulation only until its extra cost equals the present value of saved heating fuel, then they stop. But this logic, standard in engineering textbooks, omits the avoidable capital cost of the heating equipment. So I kept on adding insulation until that equipment wasn't needed. And that made the construction cost fall back to slightly below normal. The reason's simple. Subtracting the heating system saved more construction costs than I added for the super insulation, ventilation, heat recovery, and super windows that eliminated the heating system. And then saving also 90% of the electricity, 99% of the water heating energy, half the water, together all repaid their extra cost in 10 months. Not counting bonuses like the lovely central atrium seen here in a February snowstorm and its 83 passive solar banana crops so far. Somebody said I had really big earphones. Now, without needing to look like this, our house helped inspire hundreds of thousands of European passive buildings that likewise have no heating and roughly normal construction cost. And integrative design gives many benefits from each expenditure. So the central arch at the top of the upper middle image has 12 different functions, but it has only one cost. Soon after we moved into this banana farm, the Thai architecture professor Sunton Bunyatakarn visited our house and decided to adapt its integrative design approach to his own new 350 square meter home he was building in the opposite climate in steamy Bangkok. He ended up saving 84% of the air conditioning capacity and 90% of the air conditioning energy with normal construction cost and better comfort. Well, nearly everyone in the world lives in a climate somewhere between his and mine. So the simple but powerful idea using extreme energy efficiency to shrink or eliminate mechanical equipment and then using that equipment to save capital cost to pay up front for the efficiency gains, that can work almost anywhere. And integrative design keeps improving. As I'll explain, we used integrative design in 2010 to retrofit the Empire State Building and save 38, later 49% of its energy with a 3-year payback. That was considered pretty good until 3 years later, when our cost-effective Denver retrofit saved 70%, making this half-century-old federal government complex more efficient than what was then the best new U.S. office, which in turn is only a third as efficient as RMI's net positive, no mechanicals innovation center, 10 minutes from here in Basalt, Colorado. In milder but cloudier Seattle, the Bullitt Center used about as much energy as RMI's office, and now there's a Bavarian building using 2/5 less than that. Yet all these technologies existed over a decade earlier. What mainly improved, doubling the potential efficiency targets of new and old offices in 5 years, is not technology so much as design, the way we choose and combine technologies. Of the 20 most efficient commercial buildings in North America as of a few years ago, RMI's Innovation Center is the most efficient we know of in the 2 coldest climate zones. It uses about 1/9 the normal amount of energy. And like my house here, it is passive net positive and no mechanicals. It keeps people cool by 11 and warm by 10 passive methods we'll explore later. My favorite space there is the 25 square meter nega mechanicals room, where I want to sneak in one night and outline on the floor in yellow industrial tape like bodies at a crime scene where the boilers and chillers were supposed to go before we designed them out. We expect this building's cost premium and under 4-year payback would drop to about 0 payback with wider experience, as occurred in Germany's best passive designs. More on that shortly. I want to show you a nice bit of integrative structural design in the photo on the right. The whole building is curved to echo the adjacent bend in the river, so the beams that hold up the ceiling and the floor act like sideways arches, and the floors can't rack in a crosswind because the arches would have to compress. This avoids having to install X-braces usually needed to provide that stiffness against side thrust forces. Another neat trick was using cross-laminated timber structures where the grain of the wood runs in all 3 directions, so the wood serves equally well as a post or a beam. And when we were computer manufacturing those structures, we left interior channels for the sprinkler pipes, the wiring, and the air ducts, which were 1/4 the usual size because they carry only fresh air, not hot or cold air. This avoided most of the plenum height between the top of each ceiling and the bottom of the next floor above. And we used that extra height for higher ceilings with deeper daylighting, but instead, a typical office with a 23-meter low-rise height limit common in U.S. zoning could use the shorter plenum to fit in an extra 6th floor and save a 15-centimeter high strip of costly facade at each floor, all with wonderful financial results. RMI's Innovation Center was the first passive house premium building in North America, but the first in the world was this building you saw a moment ago in southern Germany. Its rooftop solar cells make nearly 5 times as much electricity as all 3 stories use. So does that mean that a 14 or so story building this efficient in a climate like Chicago or Boston could be entirely powered by its solar roof without even putting photovoltaics on the walls and windows? Well, let's build one and see. Obviously, the more efficient a building is, the more easily it can be made net zero or net positive. That's especially interesting because the Financial Times reported in 2018 that 2/3 of Germany's certified passive houses are retrofits. We'll see shortly how those are done. Now, if the super efficient approach is so commonsensical and so obvious, why isn't it widespread? mainly because of a conceptual blockage between the ears caused by an old idea. You see, in conventional practice, the more you save, the more it costs you, diminishing returns. And this notion from economic theory is deeply embedded in most decision makers' thinking, especially those with MBA degrees. In that conventional mindset, you invest in efficiency until its marginal cost equals its present valued cumulative savings. That's the cost effectiveness limit where most people stop. So when you're insulating a house, you stop at the insulation thickness that pays for itself over the years from the saved heating energy. This method is in all the standard textbooks, but it's flat wrong because, again, it leaves out the capital cost of the heating equipment. It analyzes the insulation as a component, not the house as a system. It is disintegrated design. However, if you count that avoidable equipment cost and therefore you keep investing well beyond the supposed limit, you reach a point where marginal cost suddenly decreases. For example, because as in this house, you no longer need a furnace along with its pipes, pumps, ducts, fans, wires, controls, and fuel system. But then we can tunnel through the cost barrier to achieve expanding returns, increasing returns to investment in efficiency. Why reach your super efficient destination the long way around when you can go straight to it by asking, can we reasonably design this building with no heating system? And there almost always is a way to do that. Likewise, as we'll see for cooling. HVAC equipment typically accounts for roughly 10 or 12% of the total construction costs of an ordinary office building. So getting rid of that equipment can pay for a lot of insulation and super windows and so on. After only 3 decades, this concept is becoming widely accepted in Europe, as you can see in these German and French sketches of the tunneling opportunity. Now, to learn how to tunnel, let's start with a simple design example. Most designers think of energy efficiency as kind of like picking cookies out of a jar. So if a cash-constrained developer asked her architect to suggest ways to make a new small office greener and more efficient, well, probably she'd be handed a list like this with payback times in the right-hand column. And she'd probably conclude that few or no cookies could pay back fast enough. But what happens if we optimize the whole building together? Well, if the developer chose everything on the list, the better daylighting and reduced internal heat gain would create a new ability to shift some windows around and shrink the mechanical systems for smaller loads. So most of the efficiency's extra cost would be offset upfront by the capital costs that they save. The net capital cost, just over $4,000, could pay back in a year more quickly than any one measure alone. RMI's building practice has helped design over 1,000 buildings applying this principle. For example, this bigger office in a cold place called Grand Forks, North Dakota. Smaller HVAC equipment is more than paid for upfront by the efficiency that shrinks it. So this far more efficient building costs less to construct, even though each measure by itself would not be very cost effective. Indeed, integrative design strives to exploit many benefits from each expenditure in lots of different settings, including, say, vehicles. So more on that later. Now let's dig deeper into an example of how to design a super efficient house in a hot place. This is an ordinary looking 155 square meter new house designed in 1994, 3 decades ago, by Davis Energy Group for Pacific Gas and Electric's Act Squared experiment, Advanced Customer Technology Test for maximum energy efficiency, an early test of integrative design. Its design would use about 82% less energy than was allowed by California Title 24, the nation's strictest energy code, which supposedly included all cost-effective savings. Well, you can save another 82%. Obviously, it doesn't. What's going on? Well, the site had a 40 Celsius, 105 Fahrenheit design temperature. It had an actual peak temperature about 45 C, 113 F. And yet the house achieved superior comfort with no air conditioner and lower construction cost. Dr. Richard Bourne's team first improved the floor plan and eliminated 7 meters or 11% of superfluous perimeter jaggies. Then they optimized the area and direction of the windows. They put thermal breaks into the window sashes, and they designed an oriented strand board wall that saved 3/4 of the wood, nearly doubled the insulating value, improved strength and airtightness and durability and stability and speed of construction, and it cost $2,000 less to build. Well, all of that saved 17% of the energy used on site and $4,000 of construction costs. Next, Dick Bourne's team systematically improved the lights, appliances, glazings, and hot water system, including, by the way, making the bathroom exhaust fan 5 times more efficient. It started in the 1 to 3% range, and 5x efficiency didn't cost any more. They just had to shop for it. Water cooling the refrigerator made it more efficient. It gave free water heating, and it turned the device into a summer space cooler by sending building heat down the drain. So those roughly 20 improvements together so far raised the total energy savings to about 60%, and it eliminated the $2,000-odd furnace and its ductwork. They got replaced by a hydronic radiant slab coil fed by the 94% efficient gas water heater they were paying for anyway. Why have 2 appliances when you just need 1? Well, by then, the net extra cost had risen by nearly $1,900, and any more efficiency would cost more than the energy it saved. Now what? Well, 1/3 of the original 3.5-ton cooling capacity remained. What can we do about that? Well, the designers had thoughtfully reserved a special potential cooling elimination package, a basket where they put all measures that didn't save enough energy to pay for themselves, but that did also cut cooling load. Together, 7 such measures more than eliminated the remaining air conditioning load, and of course the ducts and wires and controls to go with it. So that raised the total energy savings to 82%, and it avoided another $1,500 of construction costs. In a mature market, not a one-off experiment, PG&E reckoned this house would cost about $1,800 less than normal to build and about $1,600 less in present value to maintain. Now, despite compromises introduced by the owner, this was a real house with a real owner, it still performed so well that the neighbors took refuge in this passively cooled home during a heat storm when their 5-ton air conditioners couldn't cope. And later on, when the owner was ready to sell the house, he insisted on installing a window air conditioner anyway. He knew it would never run, but he felt that he couldn't sell it without one. Some climates are hot and humid in summer, but cold in winter. More than a decade ago, early adopters were bringing passive techniques to U.S. cities, like this New York apartment at the left built at normal cost. The architect, Chris Benefit, RA, designed it to save about 85% of the normal energy used for heat and hot water. And her practice emphasizes airtightness. Air leaks cause half the normal heating and much of the cooling load, innovative ventilation design, and working thermostats in each room to optimize the balance of gain and loss. The continuous super outsolation traps thermal mass, stabilizing indoor temperatures. All these improvements are more than paid for by dramatically downsizing the heating equipment. For example, this building's super efficient rooftop gas boiler needs only a 20-centimeter chimney. That's smaller than for many single-family houses. Her super outsulated Bronx hotel gets its hot water free from the hydronic air conditioner. Then she designed a $20 million outsolation retrofit project just completed in 9 plain old Brooklyn apartment buildings, very archetypical, to convert them cost effectively to passive house standard and all electric, saving 80% of their energy cost, all done without disturbing the occupants. That's an archetype for retrofitting the whole city's million-plus buildings and beyond. Now, New York City's carbon emissions come 3/4 from buildings. So in 2021, City Council banned fossil fuel in new buildings starting 2024. And they require buildings of over 25,000 square feet to cut carbon emissions 40% by 2030, 85% by 2050. Another outstanding example of affordable construction is in Brooklyn, a new 275-unit Chestnut Commons by Dattner Architects, one of the firm's several passive house projects. There's a recent Canary Media feature exploring many impressive New York City projects now built or underway. Another features Boston's new 812,000 square foot passive house qualified Winthrop office and apartment building, and new all-electric skyscrapers in New York City range from a 44-story apartment to a 60-story office. It's really taking off. Now, I mentioned super windows. Many good projects don't use them, but should. Super windows combine spectrally selective films on suspended thin plastic films or very thin glass sheets. So they transmit light right through, but they reflect infrared. Super windows provide 10 benefits besides saved heating energy from the center of glass insulating value. It's about 4 to 7 odd times that of double glazing. They also save cooling energy, not just in the chiller, but also in the associated fans and pumps, whose energy use varies as the cube of their flow. Super windows don't suck away your radiant heat in winter. They don't roast you in the summer, so they're important to your comfort, and they further shrink or even eliminate space heating and cooling capacity. That and the avoided ducts, pipes, and wires lower your construction cost. You don't need heating around the buildings outside the perimeter zone to combat heat loss through bad windows. Less ultraviolet comes in to fade furnishings and fixtures. The heavy gas filling in super windows blocks outside noise. The inner glass stays warm and dry, eliminating condensation that would otherwise cause mold and sash rot. And daylighting improves. Indeed, some windows can bend the light upward to bounce deeper into the building. So altogether, the greater thermal, visual, and acoustic comfort plus views of the outdoors boost our productivity, which, as we'll see later, is very valuable. To optimize performance, the best designers often tune the optical properties of the window to the direction it's facing by subtly altering details of the coatings or the glass. So it's a rich design menu, and it also helps cope with buildings that don't face in the direction you'd like. The latest version often substitutes 1/10 of a millimeter thick glass for the polymer film. I'm currently testing in the atrium here some Japanese vacuum insulation. And from a Ukrainian professor in Colorado, I'm testing a new aerogel technique that's nearly transparent. It's very hard to see. Other new possibilities include translucent aerogel-filled glass bricks, and from Sichuan University, a biodegradable aerogel made of DNA and gelatin for passive cooling, so it has 104% solar reflectance. So an integratively designed office like these should tightly meld tuned super windows with careful shading and massing, optimize structural bays and surface optics to reject solar heat. Actually, Stanford has developed some colored low-E paints, deep daylighting with super efficient direct, indirect, supplementary lighting and plug loads, no or small and super efficient HVAC with underfloor displacement ventilation. We'll get to that later. And no or almost no dropped ceiling since there are no ducts to hide anymore, only sprinklers. Well, all of this saves over half the energy without or over 3/4 with influencing tenant loads like the office equipment. The lighting and thermal and air and acoustic quality are superlative. The occupants each control their individual air and thermal conditions. That's good because different people have different needs. Reconfiguration costs are nearly eliminated when you move people around to the space. Capital cost is the same or less. Construction is about 6 months faster and much simpler. And with skilled design, capital cost often goes down, as in the example here on the left. So why would you want to do it any other way? RMI's buildings team has been proving and spreading this practice worldwide. Similar results can be achieved even in countries with tropical climates and already low construction cost. In 6 muggy Indian cities, Rohan Padikh's team at Emphasis built 1.5 million square meters of offices using 80% less energy than the Indian norm, with 10 to 20% lower construction cost, 60% less cooling capacity, but superior comfort and satisfaction. Smarter contracting and construction management were important to the cost reduction, but so is major shrinkage of the mechanicals. Glare-free daylighting, as you see on the right in that big floor plate, is delivered throughout by contract. If workers complain of glare and demand blinds, then the architect doesn't get paid. In an intriguing experiment, this building was also, as you see on the left, flipped upside down to provide shading, shrinking the mechanical investment by more than the extra structure cost. How does a developer who's a novice in integrative design get started? Well, an Idaho innovator, Gary F. Christensen, was inspired by our 99 book, Natural Capitalism, and he just went for it. He used his horse sense. He learned by doing. So he put up this 11-story Boise office tower that saved 65% of lighting energy before daylighting, 50% on everything else but plug loads, all at no discernible extra cost. The 80% water savings included innovative large area neighborhood capture. Much lower operating costs delivered rents comparable to buildings 20 or 30 years older. Turnover costs, cut by underfloor displacement air distribution shown at the lower left, fell by about $100 a square meter. But Gary didn't rest on his laurels. He told me that having saved half the building's energy, he expected his next building would save half the remainder. And he added, we don't talk of pushing the envelope. That's so last century. Our motto is stuffing the envelope, striving for nothing. And then when we get to nothing, we'll strive to do even less. We like to think of ourselves as the ultimate slackers. At the opposite end of the traditional innovation appetite, conservative real estate investment trusts, even in the intensely competitive Chicago market, like the benefits of integrative design, and they're reaping their reward in the marketplace from buildings like this. Superefficient design, whether it's new or retrofit, rests not just on big ideas, but also on many little details. For example, the Packard Foundation's 2012 office saved 1/3 of the photovoltaics needed to make it net zero energy. That was very valuable at the PV prices of that time. How'd they do it? Well, I thought their energy budget for plug loads looked high. The designer said, oh, that equipment's fine. It's all Energy Star, voluntary U.S. rating program. So we had efficiency wizard and Stanford lecturer Peter Rumsey help them shop more carefully, and that cut the plug loads by a further 58% at no extra cost with uncompromised functionality. Similar plug load diving was a key to making the photovoltaic small enough to fit on top of the super efficient bullet building in cloudy Seattle. In my own house here, the screen displaying the energy data cost no more than other equally capable Energy Star bottles at that time, but it used 1/5 the energy of the worst one on the same Energy Star list. So shop carefully and use an up-to-date list because the offerings keep changing. At Caltech, Peter Rumsey helped lead this first LEED Platinum wet lab retrofit three terms not previously much combined. Our team saved 5/6 of the energy normally needed, including 80% in cooling, 50 or 60% in the lab equipment, nearly 80% in the fume hoods air exchange, but with better safety. You know, the U.S. has 750,000 fume hoods that cost $3 billion a year to run, each traditionally using as much energy as 3 houses. Well, we'd been warned that the Caltech scientists would not let us even think about changing their equipment. But it was the biggest energy user. So as an old lab rat, I just tried asking the scientists friendly questions like, would you mind if we got rid of the noise from this little chiller in your mass spec by replacing it with a heat exchanger to that chilled water pipe running up that wall? Or if we could modernize that buzzy power supply that keeps overheating and shutting down your experiments and double the efficiency of this vacuum pump by replacing it with the more stable and reliable modern ones we use by the thousands in chip fabs, would that be okay with you? Well, it turned out the scientists sure didn't want us messing with their experiments, but they would love their equipment to work better and cost less. So saving 50 to 60% of the lab equipment was no problem. We also turned the 5-story tall light shaft for solar research, going into that observatory-like thing in the left-hand photo, into a light distributor for both science and natural illumination. It's also a rainwater cistern. It's also a chilled water reservoir that helped eliminate refrigerative cooling. This lab became an archetype for the whole Caltech campus. Now, a sunny California climate is also not necessary. In Germany, which averages cloudier than Seattle, a rigorous discipline of houses needing no heating systems has developed and spread widely now to many other countries too. You can instantly see the difference with an infrared viewer. Such heat-tight construction is supported by extensive standards, trainings, and supply chains to achieve these specific technical parameters, which certifiers confirm by independent measurement. Notice that the basic standard limits primary energy use of the house to more than triple what RMI's 2015 Innovation Center uses. Now, about 1,000 different components have been certified for use in Germany's passive house construction. For example, I've got, 3 doors like that, vacuum insulated doors called frost corks. Some jurisdictions now require such construction, and indeed, new homes in California must be zero net energy from 2020, commercial buildings from 2030. Smart developers aren't waiting. And even in mid-Scandinavia, experienced builders now put up such buildings at no extra cost. These apartment buildings in Austria and Germany confirm that passive housing can be affordable in challenging climates, similar respectively to those of Buffalo and of Chicago or Boston. Notice on the upper left, the Austrian passive apartments renting for less than many U.S. cities' poorly insulated apartments. And it's not because it's cheap to build in Austria. Such efficiencies aren't just for new buildings. The cost premium expected for diverse low-income public housing projects built to passive house standards in Philadelphia is roughly zero or even negative. But it was also negative for this lovely passive retrofit of roughly century-old buildings into affordable senior housing. Now, in Philadelphia, the 1% design temperature is -9 Celsius in winter. In summer, it's +32 Celsius with a 23C mean coincident wet bulb. Now, for non-mechanical engineers, that 9-degree summer difference, called the wet bulb depression, means that if you wrap a wet pad around a thermometer bulb, the evaporative cooling into the drier air will make it 9 degrees cooler than the dry bulb temperature measured without the wet pad. So it's a measure of the power of evaporative cooling in that climate. And therefore, an efficient evaporative cooler capturing nearly all that potential, plus a good ceiling fan, is more than you need to stay comfortable on the hottest day in Philadelphia. There's actually a startup called Montana Technologies, LLC, developing a system that harvests the water out of the air to provide air conditioning without needing a water supply. Later, we'll see what to do on days that are hot with very high humidity. Now, passive houses over tenfold thermal efficiency gains did not just magically appear. When we moved into this banana farm in January 1984, German code still allowed a new house to use about 210 kilowatt hours per square meter and year of site energy, only a fourth less than the typical housing stock at that time. Dr. Engineer Wolfgang Feist soon came to visit us in Colorado. He already knew he could use air tightness, ventilation, heat recovery, and super insulation to get probably below 50 instead of 210. But using early super windows invented 3 years earlier, we were below 25. So we needed not a smaller heating system as he had assumed, but no heating system, saving even more capital cost to pay for the super windows with construction budget left over. So Wolfgang returned to Darmstadt and built his first real passive house, then with no heating at all, the Nullenergie house, later a net zero, it's the Null Heizenergie, no heating energy house, and then the Nullenergie house, net zero in all respects. Just to illustrate his meticulous German engineering, when I visited Darmstadt, he told me that to calibrate his simulation within the last few percent of the measured daytime thermal behavior of his passive house, his last two refinements were to account first for the latent heat of water adsorbed on the plaster, and then for the sensible heat gained by water that sat in the toilet tank warming up to room temperature before it got flushed away. German engineering. State-of-the-art evolved by Wolfgang's Passive House Institute and the many organizations it spawned, including its American counterpart, the Affordable Comfort Institute, has greatly progressed. The best cost-effective retrofits, like the North German examples at the upper right, are now about 12 to 17 times more thermally efficient than the post-war German norm at the upper left. Making the whole building stock that good will occupy Germany's skilled builders for the next 2 generations. Although, as we'll see in a moment, retrofits can use labor and skill-intensive super insulation, as shown here, or super outsolation, which is often cheaper, putting a tea cozy around the building. Now, passive design in Germany has been learning for 3 decades, maybe 4. For new German passive houses, extra construction costs fell 4-fold in 15 years till 2005. Then it kept falling until it's now around plus or minus 2% if the builder knows what she's doing. So it depends on experience and skill. But the economics are widely demonstrated. They're similar or better for apartments, as in, say, Pittsburgh, or as we'll see in Europe, and in more severe climates, like even Northeast British Columbia. There's even a passive house in the Canadian high Arctic. And yet the integrated assessment models used by IPCC to inform global climate policy have not yet caught up with the market reality found in 2014 by its working group 3, showing that a decade ago, for a wide range of building types and climates, the best European new builds on the left and retrofits on the right could save up to at least 90% of the energy without needing to cost significantly more per unit of saved energy. In both these graphs, bigger energy savings are towards the right, lower costs are towards the bottom. Now, the better projects are all highly cost-effective. The big vertical cost scatter only shows the business opportunity to conform inferior projects to best practices, because whatever exists is possible. Most climate choice models assume from economic theory that retrofit costs must become high, if not prohibitive, for such big savings. I prefer data to theory. Now, Europe must retrofit about 15,000 houses a day to meet its climate goals. Thanks to a Dutch innovation called Energiesprong, energy leapfrog, industrializing mass retrofits to net zero energy and streamlining their finance and soft costs is now getting cheap enough to finance entirely from saved energy, while extending building life and improving amenity, health, and value. This 1-minute Dutch video, if I can get it, shows how an energy strong retrofit clads your house in a factory customized super insulated T-cozy and drops it in an efficient heat pump HVAC core and then a super insulated photovoltaic roof. As shown here, it can be installed even in a single day while you're off at work. A German project recently retrofitted super outsolation onto a major facade in 20 minutes. Once it's done, you pay off the retrofit cost instead of a perpetual utility bill. Then you own it, and there's a long-term warranty. More than 16,000 energy strong retrofits have been installed in Holland, Britain, France, Germany, and Italy as of about a year ago, thanks to coordinated reforms in building organizations, manufacturing, finance, and regulation. New pilot projects are now underway in New York, Minnesota, Massachusetts, California. RMI's Martha Campbell leads a consortium called Realize, RMI.org/Realize. Its aims include scaling to retrofit California's 2/5 low-income housing units and ultimately all 13.5 million housing units statewide. You may be able to post your guest lecture if you want to learn more about that, but if you're intrigued, find out about the new Global Energy Strong Alliance. That's ENERGIESPRONG, all one word. And meanwhile, this retrofit is just about done. Putting on the last bits of the super insulated facade with a lot of foam in there. They've done the photovoltaic roof. They've done super windows. And all customized to each house. You could do it for the whole row if they're identical or whatever ones. In this case, they're putting a box entry on the side of the house, a little extra living and storage space, and of course it keeps more cold air from coming in. And it's all done. You can compare it with the brick house to the left, which will use many times more energy and money. A great deal of both for European housing and what's like this, and quite a lot in North America and most of the world. This works with and without the grid. Now, looking ahead, Germany's strategies for decarbonizing its building stock by 2050 through deep retrofits and passive house level new builds finds much lower cost, total cost of ownership, than continuing to run and fix buildings incrementally. The deep retrofits turn out to have about the same life cycle cost as shallow retrofits, not a far higher cost as most economic theorists would assume. As we proved in 93 to 95 in the greening of the White House for President Clinton, historic preservation need not block super efficient retrofits. Even half-timbered Elizabethan houses in England have been invisibly retrofitted with super insulation. At MIT, Professor John Sturman first tripled the efficiency of his historic house on the Lexington Green through conventional retrofit and oil to gas conversion. Then he took it to net positive through deep retrofit plus photovoltaics. Despite heavy shading, a tight lot, and botched prior renovations, Stuart and Linda Herman in Minneapolis made their 110-year-old house 140% net positive and LEED Platinum. Unexpectedly, this raised their insurance premium by $1,000 a year because their reduced electricity use made their solar cells produce over 125% of their use. So State Farm reclassified them as a solar business rather than a household. Of course, State Farm's risk only dropped because the perils of gas leaks and fires had gone down. Such re-rating probably isn't quite illegal, but the firm deserves to look ridiculous. And meanwhile, Stewart and Linda switched over to Travelers Insurance, which did not charge more for insurance and even gave them a small lead discount. Now, many U.S. cities have run-down or derelict buildings that offer retrofit opportunities delivering social and environmental justice. In 1981, 3 brownstone low-income row houses like these in St. Louis, archetypical of hundreds of American cities, got an integrated gut rehab plus a super insulation retrofit. It was installable by their residents or by neighborhood youth without building skills or education. Nothing was assumed to be square plumber level. Everything was color-coded to snap together without anyone's having to read drawings or instructions. The retrofit cut heating needs by over 90% to $100 a year, and it cut cooling to one small window air conditioner for 140 square meters of apartment. The retrofit's extra cost was $4,700 over just the gut rehab and paid back in a few years. After 3 test homes were retrofitted, the Carpenters Union blocked further expansion, but a generation later, I ran into the head of the same union who said he was astounded to hear this history, and now he'd love to revive the project for apprenticeship and job training. The developer who launched the project is now too busy running his family firm to take this on, but if somebody else would, he would dig all the papers out of his garage. Maybe one of you? Now, evidence is accumulating that it is practical and profitable to make buildings use no more annual energy than they produce, the so-called net zero buildings, as defined by at least 15 different methods. The New Buildings Institute in Portland, Oregon, no longer tracks ultra-low energy buildings that don't have a public goal of adding renewables to get to zero net later because there are far too many of them. For North American new builds, NBI through summer 22 had registered 751 zero energy commercial and multifamily buildings spanning over 100 distinct building types, including 33% education, 23% office, 17% multifamily, and many of those are already verified or third-party certified. All of them will soon give us a flood of data on performance and costs. They span every U.S. climate zone and every U.S. state and Canadian province. They are rapidly trending toward bigger buildings. Nearly half are privately owned, so they're increasingly mainstream. The verified buildings have an average gross site energy consumption, looking back to 2020, of just 60 kilowatt hours per square meter and year. That's half what comparable existing ones use. It's about half what California's Title 24 allows. It's 2/3 greater than the RMI Innovation Center's 2019 level of 36 before it's operated fully to design intent. We're still commissioning it. Net of renewables, these buildings use zero annual energy or less. And the verified data show that some use nearly zero gross energy. So adding renewables to them would make them net energy exporters like this house or RMI's Innovation Center. A couple of other comparisons. ASHRAE, the American Society of Heating, Refrigeration, Air Conditioning Engineers, in 2020 retrofitted their 1970s office building near Atlanta, hot and humid, and they ended up using 18.5 of the gross units shown. RMI's Innovation Center in 2023 used 11.3, 11.4. It can go lower. The URL at the top of the slide includes many impressive case studies, and NBI maintains a valuable online database of diverse projects. Now, one technical caution. When you are interpreting the energy use of a single house, especially the space heating use, please remember the huge range caused by differences in individual behavior. So the 32 passive houses in this graph are all in the same city. They're measured in the same heating season, but 32 households showed heating use varying by tenfold, with a standard deviation half the mean. We see the same thing in non-passive military base housing. We've even seen the most efficient house using more energy than the least efficient house because behavioral differences exceeded the technical differences. So while each of the data points on the previous scatter chart reflects how much energy was used by a particular building occupied by particular people, you do need a larger sample of identical buildings or a well-designed experiment to separate technical from behavioral effects, and both those variables need attention. Another interesting example of the importance of behavior is Ray Anderson's book, Mid-Course Correction. His remarkable green carpet company, Interface, was holding a week-long global sales conference for 1,100 employees. The event had been irreversibly booked at Maui's Grand Wailea Resort before he found out, and at the time that was the opposite of what Interface stood for. So Ray's advisory group, on which I served, treated this as a design problem. Among the many initiatives was suggesting in each morning's plenary session a few modest behavioral changes to save energy and water without diminishing the guest experience, and then reporting the savings achieved since yesterday. By the end of the week, water and propane use had dropped 48%, electricity 21%, solid waste 34%, saving the hotel the annualized equivalent of over $1 million. The hotel became a leader in many green practices. The attendees became more mindful users of resources and spread their learnings widely. Now, I mentioned earlier that our 2010 integrative design saved on retrofit 2/5 of the Empire State's buildings' energy. How did we do that? Well, remanufacturing its 6,514 windows on site in a temporary window factory set up by the Teamsters Union on a vacant floor into super windows that pass light through but block heat, plus better lights, office equipment, air handling units, and so on, cut the maximum cooling load by 1/3. Then renovating smaller chillers instead of adding bigger chillers saved $17 million of capital cost, paying for most of those improvements and cutting the payback to 3 years, or under 1 year if we had counted non-energy benefits to the owner or tenants. More on that later. Well, then the owner went back for a second retrofit to try to save another 40%. He got delayed by the pandemic, but now he's back on track. I just visited there, and so the savings have now crept up to 49%, and he's hoping to get that up to about 80%. Now, retrofit savings can get much bigger and cheaper if they are right-timed to coordinate with routine renewals of facade and mechanicals. Here's an example of why timing matters. In 1994, a 20-year-old office tower near Chicago, where it's hot and humid in the summer and cold in the winter, suffered routine failures of its window seals, which happens about every 20 years with better quality units. So they had to put in a new glass curtain wall. And we showed that reglazing, not with like, that is identical to the existing condition, but with super windows, plus the other usual improvements, could cut the peak cooling load by 3/4. The better glazings would let in 6 times more light, 10% less unwanted heat, several-fold less noise, and they would cost a little more, $8.4 per square meter of glass. We would also retrofit deep daylighting, efficient lights whose dimming and occupancy sensors trim their use to 3 watts a square meter, and efficient power-managed plug loads drawing 2 watts a square meter. But then the HVAC system, which also needed renovation for age and CFCs, chlorofluorocarbons, could be replaced with a new mechanical system, 3.8 times more efficient, more on that later, but 4 times smaller. That could save more capital than all the improvements cost. So we ended up able to save 3/4 of the energy with a tiny net investment and a roughly negative 5 months payback compared to the routine renovation that saves nothing. By the way, they didn't do it. Interesting story of how each of the 24 parties in the commercial real estate value chain offers an efficiency business opportunity, but each can be a showstopper if overlooked. So implementation takes relentless patience and meticulous attention to detail. In this case, the owner was the largest U.S. fiduciary owner of commercial real estate. They loved our design. They authorized it for construction. But the building was actually controlled by a leasing broker short of cash and incentivized on deal flow, hence eager to roll the leases without waiting for a proper retrofit. It would take some months more. And by the time we found that out, it was too late for another 20 years. Nonetheless, the cases and portfolio tools posted at retrofitdepot.org can help achieve this right timing. It's going to take several decades to retrofit our national building stock anyway, so we may as well schedule it in coordination with other major building events, physical or financial. And that right timing could greatly deepen the savings and improve the economics. Thus, at a time of major renovation, we helped apply similar improvements at Deutsche Bank's famous Twin Towers in Frankfurt to cut its heating and cooling energy by 67%, electricity use 55%, water use 74%, carbon emissions 89%, while improving amenity and making every second window operable. Higher ceilings with radiant cooling improved daylight distribution. Space efficiency also rose by 20%, accommodating 600 more people. In one tower, smaller mechanicals freed up an entire floor for other uses. Now, innovative business arrangements include integrated project delivery to align incentives and ensure seamless collaboration between the owner, the designer, and the builder, as we did in RMI's Innovation Center to bring it in slightly below budget and schedule. Modern building information management systems to give all parties the same complete and up-to-date data at all times, and performance-based design fees to reward professionals for what they save in their design, not for what they spend. These processes are just as important as the design and technology and construction that they support and steer. And they all help to correct misallocations of capital so colossal that by 1990, the U.S. had bought $1 trillion worth of air conditioning equipment and power supplies to run it that would not have been bought if the buildings had been properly designed. Now, performance-based design fees validated by 5 RMI experiments through 2004 reward design professionals for measured savings, not for expenditures. This simple method holds designers accountable for what they can control, not what they can't control, like weather and occupancy, which get factored out by standard modeling tools. So the net result drives predictable compensation. And the best designers like this because it distinguishes them in a crowded market. Clients like it too because they can more easily find the best designers who will stand behind their work. And of course, energy and capital costs often will go down. But such fee structures remain rare. Maybe you can figure out a way to spread them. And you can even imagine going one step further, turning design from a transaction into a continuing relationship by contracting after occupancy and commissioning and measurement to pay the designers a modest fee each year as long as the building performance keeps improving. But you stop paying them if it gets worse. That's like the old Chinese wellness doctor system where you pay your doctor for keeping you well and you stop paying if you get sick. It would give the holders of the original design intent a strong incentive to keep improving technology, training, and operations for mutual benefit. Sounds like another business opportunity. We put all of our Innovation Center integrated project delivery work online as well. Let's go back to technology and design. Why is this course about whole systems? Well, because thinking that energy efficient design is about choosing and installing energy efficient equipment is like supposing that if you simply toss good ingredients in a pot and heat it and stir it up, you'll get a tasty dish. Actually, efficient systems like good cooking result from whole system design. Even the finest ingredients will not make a tasty dish unless we use a good recipe, combining the right ingredients in the right sequence and manner and proportions. So in energy efficiency, as in cooking, we need not just to use the right ingredients, but also to do the right things in the right order. Let me give you 2 examples, lighting and space cooling. Most lighting retrofitters start by installing higher efficacy, that is more light per electric watt, light sources and better controls. But if you go back to the Illuminating Engineering Society's Handbook of Fundamentals, you'll find it rightly tells you first to improve the visual quality of the task, for example, by cleaning dust out of the photocopier optics. Then improve the geometry and cavity reflectance of the space so the light bounces around better. You don't have bright things in your field of view. Then improve the lighting quality, cutting veiling reflections, that is rays that bounce right off the task into your eyes, masking the contrast between ink and paper, and cutting discomfort glare from too bright luminances in your field of view. If you kind of simulate a baseball cap and you feel your face muscles relax, there's something too bright up there. Then you optimize illuminance, the amount of light on task. Then you harvest and distribute natural light, and only then do you optimize the luminaires, the lighting fixtures, and the controls and maintenance and training. So this sequence can often save an order of magnitude more energy with better visual performance and better aesthetics. And yet most retrofitters proceed in reverse order, worst buys first, so the luminaires don't become fewer and the illumination doesn't get better or prettier. This Frank Lloyd Wright-inspired headquarters for S.C. Johnson Diversity Division is a simple early example of modern daylighting. And by the way, outside, that's a restored prairie landscape. AT&T in Illinois used similar landscaping to cut cost and toxicity by replacing grass with gorgeous prairie flowers that support pollinators, attract lots of tourists, and need no inputs. Now, this is a section view of that Johnson building showing 4 elements working in harmony to yield a 79% energy saving. Advanced glazings reduce heat and light flux across the building envelope. Light shelves, the horizontal part under the ceiling, shade the glazing and they bounce light up and deep into the floor plate. There's a suspended direct-indirect lighting system over here that is lighting mostly upward that automatically dims in response to the daylight. And then there's a raised floor for cabling, wiring, and a low-pressure plenum to deliver air to each worker under individual control. All the pieces come together ahead of schedule, under budget. Daylighting is an art as much as a science, but its technology can be arrestingly simple. This primary school in Curitiba, Brazil, had a roof overhang, you can see at the far right, that's too shallow to stop glare on the windows. So in the nearer room of the two you can see there, the glare was so strong you couldn't see with the lights off because there was too much light in the wrong place. That is excessive luminance ratios. So the iris in your eye stops down, you can't see. But adding a shade outside the window in the other room and continuing that line on the inside as a light shelf that bounced light up and along the ceiling let you see very well, still with the lights off, and save 3/4 of the electricity. That paid for the textbooks. Students also turn out to learn about 20 to 26% faster in well-daylit classrooms. So those cheap sheets of wood, cloth, or plastic to distribute daylight properly are important to democracy and development. Here's a famous Hawaiian school gently suffused with glare-free natural light, and in every picture, all the lights are turned off. In the Stop and Shop supermarket in Foxborough, Massachusetts, this simple daylighting design, saving 60 to 90% of the lighting energy, or about 8 gigawatt hours a year, cost a little more to build. Supermarkets have tiny margins, so the manager said, "Oh, we'll never do that again." But once he saw the per cart sales data, he said, "We're going to do that at every store. Look how the natural light makes the produce glow and how pleasant the space feels." So people want to come, they want to stay longer and buy more. And importantly, the design does not dump daylight into the space, but bounces it back up to spread across the ceiling without glare. You should always light surfaces, not volume. In subsequent Stop and Shop stores, a package combining daylighting, efficient lighting in cases, and photovoltaics cost an extra $500,000 and paid back in 7 months from energy savings plus the profit margin from the increased grocery sales. And remember, daylighting is only step 5 of 7 steps if you're doing the right lighting steps in the right order. The more you dig into lighting technology, the more you realize what a complex system it is. For example, dimmable electronic lighting ballasts for fluorescent lamps, that's the pre-LED technology, still widely used, have at least 18 different and often interactive benefits. Here they are. They're listed as 15, of which the 3 marked with an asterisk combine 2 benefits each. Dimmable LEDs offer many similar benefits. So either system can often save over 90% of lighting energy, but it looks better and you see better. And newer technologies will have an analogous list. Of course, to notice such multiple benefits, you need to understand the details of how that technical system works. Most lighting systems are specified not by lighting designers, but by electrical engineers or installers, electrical contractors who often lack that knowledge and therefore don't know what dimming is worth. So lighting controls are the first thing to be cut out of the design by the so-called value engineers, which means budget cutters. What they do is unrelated to value or engineering. Well, air conditioning now uses about 9% of all U.S. primary energy. Worldwide, it could soon use 50 exajoules a year. That's as big as half of total U.S. primary energy. Moreover, many tropical countries need a kilowatt of peak electricity on a hot day to cool a room. So electricity supply investments quickly eat the national budget. How can we think about this problem? How can we do the right things in the right order to keep people thermally comfortable, especially in the hot and muggy climates where billions live? Well, classically, thermal comfort depends on 6 variables. The energy design of my house seeks low air temperature, high mean radiant temperature, and medium humidity. That's healthier than hot, dry air. We also made the air and mean radiant temperatures out of phase by months to smooth out their average, which, other things being equal, defines your comfort sensation. For its first quarter century, my classic passive house had no thermostats because there was nothing for them to control. If you felt hot, you'd open the window. If you felt cold, you'd close the window. Either way, the building would re-equilibrate to comfortable conditions. Now, RMI's Innovation Center, a third of a century younger, more systematically exploits all 6 classical comfort variables. I say classical because there are others. For example, mean radiant temperature combines temperature with angular effects that can be separately exploited. Or hanging a photo of an icy blue waterfall on the wall in summer will make you feel cooler, while warm colors in the winter will make you feel warmer. Nobody quite understands that, but there's a lot of psychology going on. So how does RMI's Innovation Center eliminate its cooling equipment? Well, decades ago, I asked my hostess in Japan why she didn't heat her nearly uninsulated paper house. And she looked rather puzzled and sensibly replied, "Why should I? Is the house cold?" See, people have nervous systems and comfort sensations, but buildings don't. So we should keep people comfortable, not buildings. Therefore, the Innovation Center delivers task comfort like task lighting. Each person has a hyperchair that delivers the desired real-time comfort. It's few watts of silent fans and 14 watts of car seat heaters, all powered by a lithium battery, maintain comfort in indoor air temperatures from 16 to 29 Celsius, 61 to 84 F. Excellent ceiling fans further expand the summer comfort range by 5 to 7 Celsius degrees, not the normally assumed 3. Super windows that pass light but block heat slash the radiant loads and insulate like 14 sheets of glass. We recover 93% of ventilation, heat, or cool. So the building's kind of like an Aspen skier dressed in a down jacket and sunglasses. The building is super insulated, nearly twice as airtight as a passive house. That's very tight. And it's passively cooled by active exterior shading and natural ventilation, including automated night flush to cool phase change walls. So we don't need other passive options, nor active non-refrigerative cooling that can yield over 100 units of cooling per unit of electricity, nor do we need refrigerative cooling, nor do we need fancy storage or controls. So even in the most severe climates, this whole system approach can save about 90 to 100% of cooling energy with better comfort, lower capital cost, and higher uptime without reaching step 5 or usually even step 4. And yet, again, most practitioners pursue these options in reverse order or SPIES first. So I suggest you pause to digest these learnings so far and then consolidate them by viewing Lecture 2B, the 53-minute video tour of this passive no mechanicals net positive banana farm high in the Rocky Mountains. And then perhaps with another pause for reflection, please view the final section for this week, Lecture 2C, revealing further frontiers of super efficient design now emerging and how such buildings can create far more value than saved energy. And this is the only week in which you have 3 lectures to view. Thank you.